Welcome to our presentation on link state routing. In this video, we will explore one of the key techniques used in modern networking to ensure efficient and reliable data transmission. Link state routing is a sophisticated routing strategy that provides a comprehensive view of the network topology to routers. Unlike distance vector protocol, which rely on periodic updates from neighbors, link state routing offers more detailed and dynamic approach to routing. We will dive into key topics such as the link state database, the shortest path first algorithm, and how these components work together to optimize network performance. Link state routing protocol is a routing protocol in which routers exchange information about the network's topologies to build a detailed and accurate map of the network. This map is used to determine the most efficient paths for routing data. Each router periodically or in response to changes sends out link state advertisements to its neighbors. These LSAs contain information about the router's connections such as the state of each link and the cost associated with it. Network map. Upon receiving LSAs from all routers, each router constructs a comprehensive network map known as the link state database. This map provides a complete view of the network's topology, including all routers and their connections. Routers using the network map stored in the LSDAP, each router applies algorithms like Dijistra's shortest path first to compute the shortest and most efficient path to each destination. This ensures the data is routed via the optimal path based on the link costs provided in the LSAs. Examples: open shortest path first. A widely used link state routing protocol in IP networks, OSPF is designed to efficiently handle large and complex networks by creating hierarchical areas and using LSAs to maintain a consistent view of the network. Here is a detailed explanation of the key characteristics of link state routing. Topology awareness. Routers have a full pictures of the network's layout. They gather detailed information about each link state and cost through link advertisements from other routers. These messages include details about each router's links and costs, helping all routers understand how they are connected. Each router uses LSAs to build a detailed map of the network known as the LSDV. This map includes all routers and their connections. The LSDP gives routers a unified view of the network, essential for making precise routing decisions. Routers uses Dijistra's shortest path first algorithm to find the shortest path to every destination based on the LSDAPF. Routers quickly update each other when network changes occur, using new LSAs to share updated information. This approach helps the network quickly adapt and stabilize after changes, reducing disturbance. Scalability. Link state routing is effective for large networks because it manages and updates topology information efficiently. Protocols like OSPF use hierarchical structures to simplify management and scale effectively. Here are the pros of link state routing. Each router has a comprehensive and up-to-date view of the network topology through the link state database, which ensures precise and reliable routing decisions. A link state routing protocol use event-driven updates to promptly reflect network changes. The rapid dissemination of updates allows the network to converge quickly to a new stable state, minimizing downtime and routing inconsistencies. The hierarchical design and efficient management of network topology information make link state routing suitable for large and complex networks. Protocols like OSPF divide the network into areas to enhance the scalability and manageability. By using the algorithms like Dijkstra shortest path first, link state routing calculates the most efficient route to each destination. These advantages make link state routing a robust choice for modern network needs, providing efficiency and reliability in diverse and large-scale network environments. Here are the cons of link state routing. Link state routing protocols are more complex to implement and configure compared to the simpler distance vector protocols. The detailed network viewer and sophisticated algorithm require careful management. Each router maintains a comprehensive link state database that can consume a significant memory, especially in large networks with many routers and links. Running algorithm like Dijkstra shortest path to calculate the shortest path requires substantial processing power. This can be a challenge for routers with a limited computational resources. And finally, when a network changes occurs, routers must float link state advertisements throughout the network. This can lead to initial overhead and increased traffic as the network updates and recalculates routes. These drawbacks highlight the trade-offs involved with the link state routing, including the need for higher resource usage and complexity, which must be managed to take full advantage of its benefits. Some of the applications of link state routings are enterprise networks, ideal for large corporate networks, ensuring fast and accurate routing decision to maintain smooth operation. It is used by Internet's core infrastructure for handling complex global traffic with protocols like OSPF and ISIS. It manages heavy traffic and multiple data paths, ensuring reliable and high performance network operations. It helps service providers to manage large networks, ensuring efficient routing and quick adoption to changes. It is suitable for extensive campus networks, providing the scalability and detailed view needed for effective routing. It manages communication between network nodes, offering robustness and accuracy for reliable telecom services. These applications highlight the effectiveness of link state routing in handling complex and large-scale network environments. In this section, let us see how Dijkstra algorithm work. Dijkstra's algorithm is a classic method used to find the shortest path from the source node to all other nodes in a graph. It is widely used in the network routing protocols and path finding algorithms. Here is a step-by-step explanation of how it works. The initialization process, including setup process, setup distances, and create a priority queue. It creates a table or array to keep track of the shortest known distance from the source node to each node. Initially, set the distance to the source node as 0 and to all other nodes as infinitive. Use a priority queue or min keep to store nodes based on their current shortest distance from the source node. Initially, insert the source node with a distance of 0. Extract minimum. Remove the node with the smallest distance value from the priority queue. The node is referred to as the current node. For each neighbor of the current node, calculate the tentative distance from the source node through the current node. If the new distance is smaller than previously recorded distance, update the shortest distance and add the neighbor to the priority queue with the updated distances. For each neighbor of the current node, compute the distance from the source node to current node. If this computed distance is smaller than the known distance, update the distance. Insert or update the neighbor node in the priority queue with the new shortest distance. Repeat the process of extracting the minimum node and updating distances until the priority queue is empty. By the end, the shortest path from the source node to all other nodes will have been determined. Once the algorithm finishes, the table or array will contain shortest distance from the source node to every other node in the graph. You can also reconstruct the shortest path by backtracking from each node to source node using recorded predecessors. Let us see the example of linked state routing. Assume a simple graph with the nodes A, B, C, D, E and edges with associated weights. Set route to A and move A to tentative list. Move A to permanent list and add B, C and D to tentative list. Move C to permanent and add E to tentative list. Now move D to permanent list. Move B to permanent list. Move E to permanent list. Now tentative list is empty. The figure shows the routing table for node A. This example demonstrates how linked state routing protocol use LSAs to share information and Dijkstra algorithm to calculate the shortest path in a network. Thank you for watching.